All right, so now let's talk about covalent compounds. These are different kinds of compounds than ionic compounds, and we'll talk about why here in a second. First is just being able to identify whether a compound's covalent and ionic. And again, we're going to do that just by looking at where it lives on the periodic table. Covalent compounds form between nonmetals and other nonmetals. So both of those are going to live on this half of the periodic table, right? So something like magnesium oxide, we talked about, this is ionic because magnesium's over here and oxygen's over here. I have something from the left, something from the right. If I have something like CO2, this is covalent because both of those elements live on the right side of the periodic table. They're both nonmetals. A covalent bond is different from an ionic bond. Remember, ionic bond was all about sort of ion interactions or charge-charge interactions, a positively charged ion interacting with a negatively charged ion. But nonmetals don't form positively charged ions, right? So this covalent bonding is completely different. Covalent bonding is sharing of electrons, okay? So instead of before, like an ionic compound, basically chlorine would take all of sodium's electrons and those two ions would form that bond. In a covalent bond, so for example, in Cl2, which is between two chlorine atoms, these atoms are now sharing this pair of electrons. Okay, so covalent bonding, we think sharing electrons. Okay, so I guess the other exception, just to note here, we had that rule about, where was it? Here. Hydrogen should also be included in those covalent kind of bonding. Hydrogen's also a nonmetal, even though it lives on this part of the periodic table. So these will also form covalent bonds. And so you could have either the elements being the same, so chlorine forms a covalent bond with another chlorine atom, hydrogen forms a covalent bond with another hydrogen atom, or you could have a covalent bond formed between hydrogen and chlorine. And again, all of these represent a shared pair of electrons. One of the things that is important about these about compounds in general, actually, ionic compounds as well as covalent compounds, is this idea of law of definite proportions, which basically means that, for example, if I had a large sample, so 123 grams of carbon, and I took the mass of just the oxygen and the mass of just the carbon, I would get a certain ratio. Well, if I doubled that amount or halved that amount, the ratio of carbon to oxygen always remains the same, right? So this is sort of a long drawn out way of saying that it doesn't matter how big your sample is. So if I have a sample of CO2, and whether I'm talking about just a tiny amount or a humongous room full of CO2, the ratio of carbon to oxygen will remain the same, right? I'll always have 2 atoms of oxygen per atom of carbon. Okay, so diatomic molecules are kind of the simplest ones. These are the covalent compounds we're going to learn how to name. And they contain just 2 different atoms. Okay. There are certain elements that exist in nature as diatomic. If we look at our periodic table, our diatomic elements are this. All right, these are what are called diatomic elements, which means that if you were to find a sample of pure fluorine or pure oxygen or pure nitrogen or pure hydrogen or pure bromine, whatever, it would exist as, for example, N2, or H2 or O2. So when we talk about oxygen that we breathe in, it's not a single oxygen atom, it's actually two oxygen atoms bound to one another. The way that I like to remember these particular elements is that there are 7 of them, and they form a 7 on the periodic table plus hydrogen. Okay, so there are 7 diatomic elements. These elements exist in their pure form in nature as a diatomic molecule, so 2 bound to one another. Anything more than that is called polyatomic. All right, so now we got to get into the molecular formula versus the empirical formula. So one of the things that makes covalent molecules very different from ionic compounds is the ratio of the 2 elements isn't predefined based on what they are. So what do I mean by that? When we had sodium chloride, we know that sodium formed a +1 charge and chlorine has a -1 charge. So when we built that molecular formula, it was always NaCl. There's no such thing as Na2Cl or NaCl2 or anything like that, right? Based on the identity of those elements, the sodium and the chlorine, we already knew what that compound would form, okay? And even when it was the transition metals, we still were able to tell based on the charge of that transition metal ion. When it comes to covalent compounds, these ratios are not set even a little bit. So if I take, for example, a compound that consists of carbon and hydrogen, well, there is such a thing as CH4. There's such a thing as C2H6. There's such a thing as C3H8. There's such a thing as C3H6. You could, as far as we're concerned, the ratio of those 2 elements could be almost anything. Later on in our chemistry career, we might learn some rules as to what covalent compounds could possibly exist and ones that couldn't. But the bottom line is, just by looking at those elements, we have no idea what their ratio is going to be, okay? So a molecular formula gives the exact number of atoms for each molecule. So for example, C3H6 would be a molecule where I had 3 carbons and 6 hydrogens, right? All covalently bound together. This would look something that should be an example there. Okay. I don't want to overcomplicate things, but nonetheless, yeah. So we could tell in a molecule we have 3 carbons and 6 hydrogens all covalently bound together. That would be the molecular formula. The empirical formula is the smallest whole number ratio between those 2 atoms. So kind of a lot like our ionic formula where we reduced it just like a fraction. If we're talking about an empirical formula, this is basically taking a molecular formula and reducing those subscripts. So in this case, I could take both of these and divide it by 3. So CH3 would be the empirical formula, whereas C3H6 would be the molecular formula. Okay, this is kind of a weird distinction. I'll just say that there are some experiments that we can do that will find the empirical formula, which is why this sort of concepts exist. But really, if we were looking at that molecule, it would again have 3 carbons and 6 hydrogens all covalently bound together. Okay, but given a molecular formula, you should be able to find the empirical formula. That's really the skill that I expect you to have after this lecture. And again, you're just reducing those subscripts just like they were fractions. Okay, so for example, we're going to take a few of these molecular formulas and find the empirical formula. So glucose, C6H12O6. How can we reduce this to the simplest empirical formula? We're going to sort of find a common denominator for each one of these, or a common denominator. What would it be? Common multiple. Maybe it is a denominator. Anyway, all of the biggest number that we can divide each one of these by. In this case, that would be 6. So this would be the molecular, the empirical would be Ch2O. All right, and our next example, vitamin B is C5H5N5. That would be the molecular formula. What would be the empirical formula? Again, I'm just going to reduce those. Common divisor, that's what it's called. And that would be CHN, because I can take each one of these and divide them by 5. All right, and then lastly, laughing gas is N2O. Right? I can't reduce this any further. It's already maximally reduced. So in this case, the molecular formula and the empirical formula are the same. Okay, so now we're getting to naming naming covalent compounds. We're going to do something fairly similar to what we did before, where the first element that appears, so for example, if we're going to take an ionic compound like CO, the first element that appears in the formula, we're just going to take that name as it is. So this would be carbon. For the second one, we're going to change the ending, much like we did when it was an ion. And so for example, in this one, it would be oxide. Okay. The other thing that we have to do is specify within our name the ratios, right? Because again, those aren't something that's set just by looking at these. There's both CO exists as well as CO2. And so we're going to indicate in the name how, like those proportions. So this one would be carbon dioxide, where the di means that I have 2 oxygens. And this one would be carbon monoxide, where the mono indicates that I only have 1 oxygen. Okay, so we have these different prefixes that we have to incorporate into our name in order to specify the exact ratios, right? So again, CO, carbon monoxide, CO2, carbon dioxide. Okay. Notice that if there's only one of the first element, I don't have to put the mono in front of it. So it's not monocarbon monoxide or monocarbon dioxide. If there's only one, we leave it off. But if there was more, so if I had C2O2, this would be dicarbon dioxide. Okay, so if there's only one of that first element, you can leave off the mono. Otherwise, you're going to include that in the name as well, right? And again, the whole idea is all of these are potentially covalent compounds. We don't know the ratio of carbon to oxygen just by looking at the periodic table. So within the name of our covalent compounds, we have to specify what those ratios are. Yeah, so we did carbon monoxide and carbon dioxide. Another one would be N2O5. Well, again, I have nitrogen and I have oxide, but then I'm going to have to include those ratios, so it becomes dinitrogen pentoxide. All right, so let's do a few examples here. NF3, again, I'm just going to name the first element, whatever it is. Nitrogen. For the second element, I've got to change it up just like if it was an anion. So for fluorine, that becomes fluoride. But then I'm going to include those ratios. Because I only have 1 nitrogen, I don't have to include mono because it's the first one. But for the fluoride, I have to indicate that there are 3 of them by saying nitrogen trifluoride. Okay. N2O4, again, my first one is nitrogen. My second one is oxide. But now I have to indicate these ratios. So this would be dinitrogen. And 4, again, you'll sort of get used to these prefixes as we go. For 4, it's tetra. And instead, for oxygen in particular, because it starts with a vowel, you don't include the A's. So it's tetroxide, not tetraoxide. It's a pretty minor mistake. I'm not going to be too harsh on you guys for that, but yes. Versus if it was N2O or N2F4, this would be not dinitrogen tetrafluoride. All right, and then going the other direction, right? So we should be able to go from the compound formula to the name, but also from the name to the formula. Sulfur tetrafluoride, so I can just identify the elements involved. Sulfur, tetrafluoride, so I know that it's going to be SF. And then I'll look at the prefixes. In this case, I don't have anything in front of sulfur, so I know there's only one. And a tetra in front of fluoride, so that would be SF4. Tetraphosphorus decasulfide. All right, that sounds pretty intimidating, but I bet we can pick this apart and it's not too bad. So tetraphosphorus, phosphorus is going to be the element. And then tetra indicates that there are 4 of them. Decasulfide indicates that my next element's sulfur. And then deca, if you look back on your cheat sheet, is the prefix for 10. So this would be P4S10. Okay, so this chart here is something that you guys are going to want to know. It's really not too bad. You can flashcard it or something like that, but it's fairly straightforward. But these are 1 through 10 are the prefixes that you'll be expected to know for this course.